Welcome back. This might be our last video. At least it's kind of the last video that normally would be required in engineering when I teach engineering thermodynamics. We've got a couple videos we can do on the Rankine cycle. And like I told you, we skipped lecture 22 because I don't normally like spending a lot of time talking about exergy. Depending on where you're going, uh, the Rankine cycle may be a critical component. It might be kind of an optional component. For my class, when I teach it, I normally do the Otto cycle, and the Rankine cycle is an optional thing. But so at any rate, there will be there potentially could be some lecture 26 videos on the Rankine cycle, but this is going to be lecture 25, page one of something. We've got a long example problem here, so we'll probably have several things. This is going to be purely one long example problem video. And so we'll just get started here. If you're not used to how I do this, I'm going to write the givens out here, and then I'll go full screen when we get ready to start solving. So I've got an Otto cycle problem. So in lecture 24, we talked about what an Otto cycle is. So go back and watch that if that's Greek to you. They've given us a compression ratio here of 9.5. And they've given us some information here. They've given me prior to or before isentropic compression. So before isentropic compression, they've given you a pressure of 100 kilopascals, basically atmospheric pressure. They've given you a temperature of 35 degrees C, and they've given you a total volume of 600 cubic centimeters. And then they've given me another data point here. They're saying after the isentropic expansion. So I'm abbreviating some things here. After isentropic expansion, they've given me a temperature there of 800 kelvins. They want us to find several things. So example here, again, long example today. They want us to find quite a few things. First thing is, what are we looking for? Step one of problem solving. What are we looking for? Find the maximum temperature and the maximum pressure for this cycle. P max, T max. They also want us to find how much heat is being transferred every cycle. And they finally just ask for the thermal efficiency. Right. So far, so good. So where do we go from here? Well, it's an Otto cycle problem. Right, and they've given me some information here. Before isentropic compression and after isentropic expansion. And again, the problem statement, and by the way, I've labeled this 939. I don't know at what edition of the text, if that's out of the 7th or the 8th edition, or if I've updated it. I don't think that's out of the 10th edition, but you will probably find something like this in the Changle and Bowles text in, now it would be actually chapter 10, wouldn't it? Yeah. Yes, this would actually be chapter 10 and probably a problem number in the 30s or 40s. Again, in the 10th edition of chapter of the Changle and Bowles text, they split chapter 7 in two pieces. So now there's chapter 7 and 8, and then everything else got moved back one. So now the Otto cycle problems are in chapter 10. So again, if we read the whole problem statement, it would not be this broken down and simple. It'd be a paragraph, and we'd have to break out the parts from it. And they would say something about before the isentropic compression, it has a pressure of 100 kilopascals, a temperature of 35 degrees C, and a volume of 600 cubic centimeters. And we would need to figure out from that statement in the problem statement what that means to us exactly. So, well, if you're like me and if you've just recently been exposed to the Otto cycle and your memory is like mine, it doesn't hold on to information that well. I really have to kind of go back over it a few times. Here's a diagram of the Otto cycle here on the right compared to a normal spark ignition cycle. But notice that my expansion and compression are these top and bottom lines, and they're labeled isentropic. So this is our Otto cycle over here. And The isentropic compression is going from 1 to 2. That's where I'm decreasing the volume. That's compression, decreasing the volume. And so they're saying before the isentropic compression, well, if that's going from state 1 to 2 and it's before that, that means these are properties at state 1, according to this diagram here. And then after the isentropic expansion, so that's expansion goes from 3 to 4, where I'm going from a small volume out to a large volume. So after that process, that is state 4. So I'm going to label that temperature there as T4. So it's important we know what the problem statement is telling us. That is a wonderful skill as any engineer. You're always going to be talking to clients or whoever you're solving problems for, or your manager, and they're going to give you kind of vague description of what needs to happen. And it's going to be up to you as an engineer to figure out, okay, what the heck does that actually mean? And how do I translate that into something that allows me to actually go out and solve the problem that needs to be solved? That's, I get all that to say, if you're looking at like Steve, I don't want to read paragraphs and try to translate those. Well, this may not be for you. There are plenty of other majors where you might not have to do that. But this is probably not one of them. Just trying to be honest with you. I'm not trying to run anybody off. I know I had one time student complain on my course evaluation for professors, says multiple times, if you can't do this, you shouldn't be here. Well, in our line of work, we can kill people if we don't do things right. So anyway, I digress. Let's try to solve this problem, shall we? So first step is what are you looking for, right? General problem solving. We've talked about this multiple times throughout the semester. What am I looking for? These are the things I'm looking for. Okay. Um, what is known? Well, we got to organize that from and just went off on a tirade about, taking information that's not clear and trying to make it clear about what do you know and what does that actually mean to us. And then what tools, laws, or relationships can I use? And that's one of the challenges with these Otto cycle problems is there's a whole just wealth of tools I can use to try to solve an Otto cycle problem. We need to organize that information now, right? So let's try to do that. First and foremost, notice what is T max and P max? Where do those occur? And I'm just going to draw kind of roughly the Otto cycle diagram so we can refer back to it here. State 1 is up here, and you're going to compress to state 2. So this is 1, 2, and then we go constant volume heat addition is state 3, isentropic expansion down to state 4, and then constant volume heat rejection from 4 to 1. And the diagram typically includes Q in and Q out. Workout is occurring on top because it's expansion. Work in is occurring on bottom. That's compression. Talked about that back in chapter 4. So and this is pressure with respect to volume. So where does the T max and P max occur? Well, for sure, you can see from this diagram, P max is this point right here. We know for sure that's going to be P3. T max is most likely state 3 because if you look at what's going on here, I'm holding volume constant from state 2 to 3, and I'm dumping a whole bunch of heat into it. And this heat in replaces the combustion process in a normal combustion engine. We're replacing it with just a simple heat addition process. So if I hold the volume constant, I dump a whole bunch of heat into it, that's most likely the point where I'm going to reach a max temperature. I'm going to put a question mark here because we don't know for sure yet. The good news is I already know 2 temperatures. So if I know T2 and if I can find T3, or if I can find T2 and then find T3, I have all 4 temperatures. I can compare them all to each other and absolutely know that T3 will be the max. And typically in an Otto cycle problem, you'll want to figure out as quickly as you can how to get to all of the temperatures around the cycle. So with that in mind, before I start trying to tackle these things, I normally find, and you wouldn't necessarily have to do this when you're solving this problem out, but I do find that it's helpful when I'm first explaining an Otto cycle problem Let's talk about the four different states, right? And we did something like this when we talked about isentropic efficiency because there were three different states there. And we talked about what do we know about each of those three states and what's related, what's constant. It just basically I find when I'm trying to do this in a classroom setting, it gives everybody a chance to kind of get on the same page about what do we know about these different states? Because we actually know quite a bit already, right? They've given me P1, T1, and V1. That's given. So P1, T1, V1. That's known. And they've given me T4. That's known. Now, here's where and this sometimes, I don't know, maybe I think for students, sometimes this might be a bit painful process that I go through in class where I just ask, okay, what else do we know? And I'll wait until I start getting some answers. And if I wait for a while, I might ask some more prodding questions. This is just kind of being a seasoned instructor. I might ask questions about, okay, well, if I don't get a lot of good answers, I might say, well, what's constant? What things are constant between different states? Right. And sometimes students, before I get to the what's constant between states, students might offer up, well, can we use ideal gas law? Yeah, you can. Again, we talked about an Otto cycle in the last lecture, lecture 24, that we're going to treat the substance in this pretend internal combustion engine, idealized internal combustion engine. We're basically going to treat it as a piston full of air that we're going to heat up and cool down, expand and contract. So I have air that we're going to treat as an ideal gas. So yes, ideal gas law would apply between all four states. Now, so that's a tool that we'll use moving forward. But that doesn't necessarily give me any specific properties about any particular states. It just gives me a way I can relate properties to each other. So it's a tool we'll use. We'll come back to. So again, I would ask my class, we're just sitting here staring at this and they're staring at the board and uncomfortably hoping I will give them the answer, and I won't. I'm just going to wait until they give me answers that we like. And I'll ask what's constant between some of these states? What properties might be constant between some of these states? And I might kind of motion towards the diagram of the Otto cycle, and somebody might say, well, is aren't the volumes constant at different points? Yeah. V1 is equal to V4, and that means V4 is equal to V1. And since I know V1, that's a known value, that means it's the same at state 4. All right, and I might say, okay, well, what else is maybe constant? And somebody might say, oh, well, you know what? V2 is equal to V3, and V3 is equal to V2. Yes, that is correct. Now, I've moved this down because there's an important bit of information in our givens that we haven't looked at yet. Very, very powerful bit of information in an Otto cycle is this guy, the compression ratio. If you don't remember what the compression ratio is, I would encourage you to pause the video here, go back to your notes of the last lecture of lecture 24 and consult. What does this compression ratio do for you? And I would say pause it and and bring that back here because that's very important what the compression ratio does. All right, you got it. So normally somewhere off to the side, I would, kind of on another sideboard, I would write, remember, compression ratio is the ratio of the maximum volume to the minimum volume. And notice from our diagram here, there are two max volumes and there are two min volumes. So any combination where I've got a max volume on top, that could be 4, and a min volume on bottom, that could be 2. And so I could have 4 on top and I could have 2 or 3 on bottom. And instead of 4, also a max volume is state 1, so I could have 1 on top. And I could have 2 or 3 on bottom. Any combination thereof is going to have the same value, 9.5. So what does that mean? That means that since I know V1, I also know, and I know the compression ratio, that means I also know V2, right? So I also know V2 is equal to V1, which is known, divided by the compression ratio. So I can actually find a number for that. And that means I know the volume at all four different states. Okay. So that's a very important bit of information. Another very important bit of information, again, the ideal gas law is going to be useful. But then I'll also say, okay, well, is there anything else that's constant? Any other properties that are constant between some of these states? And I won't give it to them, but I might maybe motion ambiguously towards this word here, which I've abbreviated, but that's isentropic. And I might, do something like, well, is there anything maybe that's constant between for these? We've talked about volumes constant for these processes. Is there anything constant for these isentropic processes? Right? And I might emphasize isentropic a few times. Is there anything constant for an isentropic process? Yes, there is. Um, Isentropic by definition means the entropy is constant. So if it's isentropic expansion between states 3 and 4, that means the entropy is constant between states 3 and 4. And the same thing for the isentropic compression between states 1 and 2. Isentropic means the entropy is constant. And if it's isentropic compression, that means that the entropy is constant between states 1 and 2. All right, so this is normally the information I would put down on the board. Again, excuse me. You wouldn't have to do this step every single time you solve an auto cycle problem, but it's not a bad idea. And if it helps you, by all means, please do it. I definitely find first time out, it definitely helps people kind of organize, at least in their head, what the different states and phases are, what they do for them. Excuse me. All right. So what do we do with that? Okay, let's go back. What the heck are we looking for? I need to find T3 and P3. Now I can find heat in probably if I know information about state 2 and 3. Well, right now I don't know any information about state 2 or 3. So since the heat in occurs between states 2 and 3, I'm going to need to know about state 2 and state 3 to try to figure out what goes on to get from one to the other, which is the heat. But I know information about states 1, a lot of information about state 1, a little bit of information about state 4. But I actually know a whole lot. That's what the whole process here is, organizing. Okay, there's a bunch of information. Just the fact that it's an Otto cycle. There's a whole lot of information you also know. This kind of organizes it a bit. So with that in mind, if I need to try to find T3, how could we go about that? And somebody might say, a lot of times, one of the first things somebody might say is, well, what about the ideal gas law? Okay, let's look at the ideal gas law, right? P1 V1 is equal to MR T1 because I have total volume. So let's use this form. Also, I don't know the mass right now. A keen eye might say, well, Steve, you know all of those. The only thing you don't know is the mass. That's actually correct, and we'll need that later. This will give you an opportunity to find the mass because I know P1, V1, and T1. Mass becomes my only unknown there because I can go look up the R value. But what I like to do, a very powerful thing to do with the ideal gas law, if you're working between multiple states, is if you'll put your constants on one side of the equation. So mass is constant, it's a closed, sealed piston with air in it, and the R value is constant. And it's the same for all air. And then what I can do then is I can set up the same ratio at all the other states. P2 V2 is equal over T2 is equal to P1 V1 over T1, which is equal to MR. And the same thing at states 2 and states 3 and 4. P3 V3 over T3 is also equal to P4 V4 over T4. So again, I know P1, T1, and V1, which means I can find M. That means I know M times R. That's the same as this ratio. So I know what this, at state 3, I know what this ratio is equal to. It's equal to P1, V1 over T1. But the thing is I don't know P3 or T3. Now I can find V3 because V3 is equal to V2, and V2 can be found through the compression ratio. So I know V3, but I don't know P3 and T3. So that's, in this case, here's just one equation. This ratio is equal to that ratio. So that's one equation with two unknowns. I can't solve this yet. But if I know P3 or T3, I can use ideal gas law to find the other two. So I need either P3 or T3. If I have either P3 or T3, that will allow me then to find the other one. So I need to, based on what I know, I need to somehow find either P3 or T3. And I can use ideal gas law to find the other one. And then I'll wait. I'll wait. And sometimes it gets to be uncomfortable silence, and that's where a seasoned instructor will thrive, is waiting until I get an answer that we like, that we can move forward with. And maybe I'm trying to replicate that a bit here, although all you got to do is fast forward a little bit and can bypass that. But here we are. You're still listening. So that means either you're not uncomfortable enough to try to find an answer, or you're sitting there screaming the answer at your screen, and the people around you are wondering why you're screaming at your phone or your computer. This guy's helpful. Sorry, I need more. This guy's helpful. How is that helpful? Well, if you like putting organization tabs in your book, see, I put one in here, but it's broken off. The chapter 7 summary is a nice place to put one. I got to try to wedge this in here. Remember, we said that if you have an ideal gas, and I'm sorry this is not completely in focus, but if you have an ideal gas and it's isentropic process, the chapter 7 has these really powerful ratios. I call them the K ratios, very powerful set of equations that are easy to implement. Now, I think I've mentioned this, and if I haven't mentioned it, I really want to mention it again. Remember, when you see equations that are this simple, describing very complex phenomena, big red alarm bells need to go off in your head saying, what are the rules? Equations don't get this simple unless there's rules involved. The rules are this. It has to be an ideal gas. Well, we've got an Otto cycle, so it's an ideal gas. It has to be an isentropic process. Well, I have two states where I have isentropic process between states 1 and 2 and states 2 and 3. Now, those equations are written for a process from state 1 to 2, but we're not limited only to states 1 to 2. Now, it does work in this case because the entropy is constant from state 1 to 2, but you can think of those subscripts as more generic. In fact, you really should start thinking about subscripts as more generic than just always 1 and 2 or final and initial or whatever the case may be. As it's written, these equations here is for isentropic and ideal gases. And there are some situations where I have that we just defined. If it's isentropic and an ideal gas, I'm just going to use random subscripts here. I can say T square over T circle. In the book, it says state 2 to state 1, but I'm going to use a more generic subscript than that. You can use X and Y if you like, is equal to the ratio of V. In the book, it's 1, so I'm going to use circle, divided by V square, because in the book it's 2. And the exponent here on the ratio of volumes here is K minus 1. So what you can do is from 3 to 4, it's isentropic. S3 is equal to S4. So from states 3 to 4, it is, in fact, isentropic. So I can say that T3 over T4, and notice how the subscripts flip on this other side of the equation. So I just need to do the same thing here, is equal to specific volume 4 divided by specific volume 3 to the K minus 1. And if you're paying attention, you should be saying, well, Steve, those are specific volumes. That's not volumes. And again, the rookie mistake is to treat them like speeds. That's hopefully you're not still making that mistake. Um, these are not speeds. These are not total volumes. These are specific volumes. However, notice that by definition, the specific volume is the ratio of total volume divided by mass, and it's a constant mass because it's a closed system. So it's the same mass, top and bottom, which means if the mass is constant, the ratio of specific volumes is equal to the ratio of total volumes. And that's something I think we've mentioned before, but it bears repeating. Oh, by the way, R is V4 over V3 because that's a max volume over min volume. So for this very specific scenario, because we've been very careful how we've derived this, and because we're good engineers, we understand how the derivation works, even if we don't do the derivation ourselves, we know this works. That's pretty cool, right? T3 is equal to T4 times the compression ratio to the K minus 1. For an Otto cycle, that expression is always true. If you're just letting AI do this for you, or you're just following some solutions manual or some solution service, they're just going to give you this equation and you have no idea why that's true or if that's true or if you should be using that. In our line of work, that's how we kill people. We use the wrong equation for the wrong situation, but we didn't do that because we understand why this equation works and we've derived it ourselves to verify that whatever this random source is giving us is in fact correct. So all that to say, now I can find T3. T3, feel free to, I thought about pausing here, but we'll go ahead and run this through because this shouldn't take too long. This is, okay, yeah. I was looking at this I'm not used to using this calculator too much. In fact, it's a little dark. I'm just going to use my phone calculator that I'm used to using. Well, I know shows up really good on the document camera. This is just, I use an app called Real Calc, I think it is. I don't think I've ever mentioned that. Okay. I'm on Android. No. Not getting the text message. It's fine. Okay. This is 800 kelvins times compression ratio was given to us as 9.5. And by the way, what is K? Ooh, I'm going to go all the way back up here. I'm going to make an assumption. We're going to assume cold air. What does that mean? Move down here because I don't have a whole lot of room up there. Using the cold air assumption. Using the cold air assumption. There's this table in your text, table A2A. Table A2A, ideal gas specific heat properties at 300 Kelvin. I try to make it very clear throughout the semester, don't use this table. Until the very end of the class, don't use this table. We're at the end of the class. We're using the cold air assumption because how often are we at 300 Kelvin? Very rarely are we at 300 Kelvin. We're not at 300 Kelvin throughout the cycle. However, this is what we call the cold air properties. So if we're making the cold air assumption, a valid assumption we would normally make for the Otto cycle, not good for like chapter 7 problems. So if you're using these properties in chapter 7 problems, you're losing some points with me. If you're doing it multiple times, you're starting to lose a lot of points, but that's another story. Here we've got air, and they've given you the gas constant, C sub P, C sub V, and K. So I'm going to go ahead and copy these down. Right? So we're in metric units. So the R value, which is always constant, the R value doesn't change, but that's 287 kilojoules per kilogram Kelvin. I don't think we need C sub P. I'm only going to copy down C sub V. I'm almost certain that's all we need. C sub V is 0.718 kilojoules per kilogram Kelvin. And the K value, which is the ratio of C sub P to C sub V for air at room temperature, is 1.4 even. 1.4 is normally a good first guess for K. And the advantage here of making this cold air assumption is we don't have to do any guess and checks. We don't have to use table properties unless we just really, really want to. We're acknowledging that the Otto cycle is just a rough estimate for an internal combustion engine. And so 2 significant figures would be sufficient. And that's what we're going to get with a K value of 1.4. So 1.4 minus 1 is going to be an exponent of 0.4. So I've got 800 kelvins multiplied, and let's actually do this first. Let's do 9.5 raised to the power of 0.4 equals, and I need to multiply that by 800 kelvins. Massive temperature. That's expected. This is after we've dumped a whole bunch of heat into it. 1,900 and roughly 70. We'll say 69 kelvins. Okay. That's going to be T3, at least our estimate based off the cold air assumption. All right, are we done? No, remember they asked for a whole bunch of things. They also asked for P3. Now remember, you can do one of 2 things. If you knew P4, you could use, there's an isentropic K ratio that involves ratio of pressures. I think the ratio of pressures is equal to the ratio of volumes to the power K. If I knew P4, I could use that to get it, but I don't know P4. But we did say, hey, using the ideal gas law, now that I know T3, I could also find P3. So that's what I'm going to do. I'm going to use the ideal gas law to find P3. So we're going to say that P1 V1 over T1 is equal to P3 V3 over T3. And we're going to solve that out for P3. So P3, and I'm going to group like terms together. So I'm going to group, that means I'm going to put V1 over V3. I'm going to put T3 over T1. And then I'm going to put P1 by itself. And notice that V1 over V3 is the compression ratio. So numerically, to solve it out, P3 is equal to the compression ratio, 9.5, times the ratio of temperatures. T3 is the numerator, 1969 kelvins. I would ask my class, okay, what is T1? And it's written on the board normally, and one of the other boards, and somebody will say, oh, it's 35. Okay, so what is T1? Well, it's 35, right? No, it's not 35. Not for this equation. There are only certain instances where I can use T1 of 35. I think I can do that in my head, but let's just do it. 273 added to 35 is 308. I have to use Kelvin or Rankine in this instance. And since we're in metric units, we're going to use Kelvin. 308 kelvins is T1. And then P1 we said was 100 kilopascals. Okay. So 1969 divided by 308, that's going to be roughly 6. Yeah, 6.4 multiplied by 9.5. So it's going to be like 60. And then times 1,000, or I'm sorry, times 100. So be about 6 megapascals. 6,000 kilopascals are about 6.07 megapascal. That'd be P3. We know this is P max. We absolutely know this is an answer for P max. I have no reason that we can see that this is higher than the 400 Kelvin that I've, or I'm sorry, the 800 Kelvin I've got at T4. I have no reason to believe that this is going to be lower than T2. Right? We expect this is going to be higher than T2. Why, Steve, why do we know that? Well, go back and look at the diagram. What's going on to get from state 2 to state 3? T2 is the only unknown temperature right now. They want to know what is the maximum temperature. We think that's at T3. I know these other two temperatures. I've just found T3 is much higher than either of these other two. I don't know this temperature, but I'm dumping a whole bunch of heat into this thing to go from state 2 to 3. Odds are pretty good this is my max temperature. Now, the good news is I'm going to know that for sure here in a little bit. Why? Well, it's because the next thing they're asking for is the heat in. They want to know, problem wants to know, what is the heat in? Okay, well, where does the heat in occur? The heat in occurs here from state 2 to 3. Okay, so to find heat, to find the heat in, I would go with my normal question. Where do we start? This is my unknown. This is what I'm looking for now. What's a good law, tool, or relationship or expression I could maybe use to find an unknown heat transfer? And I genuinely hope at this point the gag reflex is the first law. Yes. First law. From 2 to 3. Hang on a second. I'm going to get a phone call here. In this modern world, it is really difficult to block out all the distractions while you're trying to record a video. Thanks for suffering through that with me. First law from state 2 to 3, because we're needing to find this heat transfer. How do we do that? Well, you draw your system. Same process we did starting all the way back in chapter 4. Introduced briefly in chapter 2. You draw your system. It's a piston. From state 2 to 3, go back and look at our diagram. Remember, this is a constant volume heat addition. So there's actually, normally with a piston, we would say there's boundary work. But in this case, because the volume's constant, there's actually no boundary work. So the only thing crossing the boundary right now is going to be Q in. So it's a closed system. So the first law says add the ins, subtract the outs. Well, it's just Q in. There's no work and there's no mass crossing the boundaries because it's a closed system. So that's the only thing I've got there is heat going in. And that's going to equal the change. So in minus out equals change. So the change for a closed system is delta U. It's constant mass, so it's just mass times delta U. I have an ideal gas. So what I would do is I would approximate this as MC sub V. It's not, I apologize, it's not from 2 to 1. It's from final to initial, it's from final minus initial. I'm ending at state 3 and I'm starting at state 2. So this is from 3 to 2, or from 2 to 3. So that's the subscripts we need to be using here. Okay. So this is what I'm looking for Qn. I've got an equation here. Qn is equal to mc sub v T3 minus T2. Sorry, my subscripts are scribbles there. I know C sub V because I'm assuming cold air. I know T3 because I just found it up here. So I have a value for C sub V and I have T3. I don't know the mass and I don't know T2. So now I have one equation with 3 unknowns. Now you might remember I said earlier, oh yeah, back here we could use ideal gas law because I know all the properties at state 1. I also know them all now at state 3, or I could find them all at state 3, but I know them all at state 1. So I could use this to find mass. Okay, that's good. So mass is going to equal P1 V1 divided by R T1. So that'll give me the mass. I know C sub V. I know T3. I need to find T2. Okay. Go back to our problem. Say, all right, what do we know about state 2? What do we know about state 2? We know the volume is the same as 3, and we've not calculated either of those, but we could find them. And I'll wait when I'm in class until somebody offers up a suggestion. And normally I don't have to wait too long. Normally somebody will say, well, can't we just use, we use this for state 3. Can't we do the same thing for state 2? Yes, actually we can. Remember this guy. Temperature at one state divided by the temperature at another state. If it's isentropic and an ideal gas, we have that from 2 to 1, is equal to the inverse ratio of their specific volumes. And so you see what we did from state 3 to 4. We can do the exact same thing from state 1 to 2. We can say that T2 divided by T1 is equal to the ratio of V1 to V2 to the K minus 1, which since the volume at state 1, again, the ratio of specific volumes is the ratio of total volumes. The volume at state 1 is a max. So it's a max divided by a min. So it's just the compression ratio times K minus 1, or to the power of K minus 1, I should say. Okay, so that gives me a clear path to find all the unknowns here. I'm going to pause this because this is getting really long. I'm going to calculate this out. I would tell you to do the same thing. Pause it here, calculate these values, come back, let's compare. Okay? All right, how'd you do? Here's what I've got. Now, common place that people might mess this up is your total volume. We said it was 600. That's 600 cubic centimeters. Make sure you're doing the correct conversion to go from cubic centimeters to cubic meters. So you got to divide by 100 3 times because it's cubed. It's not 100 cubic centimeters in a cubic meter. It's 100 cubed cubic centimeters in a cubic meter. That's a common place people will mess that up. So you can see I've got my mass there, my temperature 2, how I calculated 0.59 kilojoules per cycle for this process. All right, goodness, Steve, are we done yet? I don't think so. We still have, what do we got? We got 2 of 3. I'm sorry, we've got 3 of 4. 3 of 4 things. What else are we looking for? The efficiency. Efficiency is, there's a bit of a cheat code for the efficiency, but let's start with kind of the normal is, okay, how do we find efficiency? And somebody might say output over input. And that's because our text loves output over input. And that's fine. Okay, it's what we want. The net work out divided by what we have to do to get it, Q in. But there's a bit of a cheat code for this. This is for an Otto cycle, it is 1 minus 1 over R to the K minus 1. It's pretty cool. And so we can actually find this right off. Right? So you can calculate it right now. 1 minus, no, let's do this. 9.5 to the power of 9.5 to the power of 0.4. Using 1.4 for K. Need to invert that. And then apply a negative sign and add that to 1. About 60%. 0.59, we'll say 4, or 59.4%. Now, I do want to show you one last thing here. Technically, we're done. Technically, that's all the answers the problem asked for. I do want to show you one last thing here. Right? This thermal efficiency being the net work out. That's the difference between work out and work in divided by heat in. Well, this would be the work. It's expanding from 3 to 4. It's being compressed from 1 to 2. And the heat is going in between states 2 and 3. Now, we've already done the heat in from state 2 to 3, and notice what we did here. So how do we find the work? Well, we do it the same way we just did that. If we wanted to find from state 3 to 4, If I wanted to find the work out from here to there, now what do we have going on there? Well, this is isentropic expansion. It's work out. This piston is expanding and it's isentropic, so there's no heat transfer. It's reversible and it's adiabatic for it to be isentropic. So I've got the work out, which is minus the work out because it's going out, is equal to m, and this is from 3 to 4, so it's u4 minus u3. So the work out, which is equal to the work from 3 to 4, and I'm going to distribute my negative sign in here. This is going to become m times u3 minus u4. And again, somebody will ask, why'd you flip these? I'm distributing the negative sign to flip those. Hopefully that helps. If not, feel free to ask it in the comments. That's mc sub v times T3 minus T4. Okay. And I know all this, right? I know the mass, I know C sub V, I know T3 and T4. So we can actually find those. Not going to, but you could. And then from 1 to 2, it's the same basic process. I've got this piston. It starts out down here at the bottom dead center, and we put work in to compress it. Oh, sorry, you can't see that. I put work in to compress it. It's isentropic, meaning it's adiabatic and reversible, or at least that's because it's reversible, we know it's adiabatic. All these processes are reversible. So first law here says, well, I've got work in, there's no heat transfer because it's adiabatic, is equal to m, and it's going from state 1 to 2, so it's u2 minus u1. And this becomes mc sub v T2 minus T1. So why am I doing this? I'm plugging these in here for the efficiency. Thermal efficiency. Going to be work from 3 to 4, which we found here. That's mc sub v T3 minus T4. Minus the work in. It's the net work out. So it's the work out minus the work in. So this is mc sub v T2 minus T1 divided by the heat in, Qn is mc sub v T3 minus T2. Notice mc sub v is constant and on both top and bottom. So this becomes T3 minus T4 minus T2 minus T1 divided by T3 minus T2. Notice for a reversible cycle, the efficiency of the performance is only determined by the temperatures through which this cycle passes. Kind of neat. Again, this is how we calculate it. The simplified version, just simply specific to an Otto cycle, this expression works. This always works for any thermal efficiency, but specifically for an Otto cycle, this is how you would find it. All right, guys, that's what I got. Enjoyed the course. Again, if you need the Rankine cycle, I'll make videos available for that. That's going to be lecture 26, so you should be able to find that. All right, guys, I'm going to stop there.